It's a privilege and an honor to introduce our first speaker this afternoon, Jack Marr. He's going to answer the question, what good is mathematics? Now, this may sound like a trivial question, even this audience, but if you bear with me and fly back 400 years and get to the dawn of the 17th century, perhaps you could listen to the following dialogue going on between two scientists. One saying, why do objects fall? Well, don't we all know it's because of gravity? And this other scientist replied, well, we know the name of the thing, it's called gravity, but perhaps we really don't know what it is. We don't know how it relates the speed of falling to time, is it to space? Perhaps what good is mathematics is also one of those questions that may sound trivial, but may not be as trivial as that. In fact, another scientist of the time, Johannes Kepler, he still adopted the concept of force that was popular at the time, and that assigned force to sort of an intrinsic property of a body. But when he discovered the second law, historically it was the first to be discovered, started to realize that apparently, force could not be this intrinsic property. And how did he discover that? Well, part of the story was that he discovered that the speed of the planets was somehow related to the distance they had from the sun. So they would go a little bit faster when closest to the sun, and a little bit slowest when they were further apart. So it was when relating and quantifying these variables that somewhat this mystical conception of force started to give way to our modern conception of force. So mathematics plays an important role, but this is the job of Jack Marr to tell us about. So who is Jack Marr? Well, he's a good colleague of ours. You all know him, but let me say nonetheless a few things. He obtained his Bachelor of Sciences degree in Georgia Tech, not in one discipline, not in two, but in three. Psychology, physics, and math. And then he moved on to the University at Chapel Hill, North Carolina, Chapel Hill, where he obtained his PhD in experimental psychology with a minor in physiology. Then he moved to Georgia Tech, where he has been professor since then. I didn't know, I was just commenting with Jack, that I didn't know he had been one of the founding fellows of Association for Behavioral Analysis. He has been the president of that association, and the past president also of the Society for the Advancement of Behavioral Analysis, of Division 25 of APA. He's the current review editor of SQAB. His interests are very diverse. Just to give you a sample, something that intrigued me, some of his research on low-frequency magnetic fields and their influence on operant behavior. But other things, interest in dynamical systems. He has written on the development of instructional systems, creativity, automaticity. I remember a talk that he gave some time ago. Very nice talk. So this is a very rich set of interests and competencies. Please join me in welcoming Jack Marr.
Thanks very much, Armando, for a very kind introduction and also for the privilege of being able to speak before this group. Can everyone hear me? What? I see this talk is a bit lighter than I had anticipated. To discuss mathematical modeling as applied to behavior analysis is a multiply daunting task. First, most behaviorally trained audiences have little formal training in mathematics, and aside from that, such modeling, indeed perhaps any modeling as is commonly thought of, has been seen by some to be antithetical to a behavioral approach. On the other side, mathematical topics and approaches are in fact difficult. To assert otherwise is a reflection of both arrogance and ignorance. Mathematical training is somewhat like musical training. Long hours of intense and devoted practice, sometimes frustratingly fruitless, and no one can even begin to learn anything like the entire repertoire. Also, as in music, Only a very few achieve real accomplishment. And even to the serious amateur, the performances of this elite can seem like magic. Many, and I certainly include myself in this group, who've had some formal training in mathematics are like devoted sports fans, aware of some of the rules, techniques, strategies, and skills needed to play successfully, but must be largely contented to sit in the stands and watch the game played by gifted experts. There's also the problem of selection, because to begin to discuss mathematical models, even in a field like behavior analysis, requires very considerable selection from an enormous repertoire. My primary purpose today is to provide a quite general overview of the enterprise of mathematical modeling, in particular as it's been applied to problems of phenomena behavior analysis and some related areas. In this context, I'll try to sketch along the way some examples of these approaches without, I hope, bogging you down too much in any mathematical detail, just enough perhaps to give a flavor for the techniques. My intention is not to focus on any particular model or approach, but rather to give some sense of the scope of the enterprise and the enormous range of activities and interests comprising the modeling business in behavior analysis. I should first address the questions. What are models? What good are they? And that is, why might we use or need them? There are many kinds of models. For example, any metaphorical description, including poetic, might be considered a model in the sense of capturing some selected features of a presumed essences of a phenomena. We're also familiar with scale models of trains, planes, and automobiles. These kinds of models can have special uses in engineering. For example, models of structures such as airfoils may be tested under controlled conditions and their performance evaluated in scale to judge how they would behave under actual conditions of flight. Of course, there are also various kinds of animal models of significant human behaviors, like anxiety, depression, drug abuse, and so on. Another sort of model is common in cognitive psychology, a conceptual framework attempting to identify constructs, intervening variables, and interrelating processes characterizing some cognitive function, for example, memory or attention. Typically, these kinds of schemes are what I would call metaphorical mediational models. They're conceptual bridges between certain environmental and historical initial and boundary conditions and behavior. Models of this type are often examples of what I will examine later as models based on models. A memory model based on a computer system is an example. The typical block diagram of computer functions is of course, itself a model, as would be the electrical circuit diagram for the computer. All these contrivances are kinds of maps, where at some scale there's a one-to-one correspondence between a picture and a function, place, process, or device. A map of Boston is a model in this sense. Finally, we should not forget the entire enterprise of behavior analysis as a model of human and animal action, reducing it to schemes such as the effects of contingencies in their history. Today, my focus is upon certain classes of scientific schemes called mathematical models. A mathematical model is a simplified but formal description of the world that attempts to capture putatively essential properties of a phenomena for the purposes of analytic and empirical exploration, including accounting for extant data and the prediction of new data. Distilled to its essence, it's a set of assumptions put into the abstract language of mathematics about some phenomena of interest. This formal language consists of a collection of abstract symbols together with a set of rules for manipulating or combining those symbols to create new symbols and symbol strings. In addition, one must begin with a particular set of symbol strings or statements called axioms that are assumed to be true. Given these, along with the rules of logical inference, we may then generate new true strings or statements, and these are called theorems. Proceeding in this way, whole systems of mathematical methods can be created to form a framework for constructing models of the world. Such models may be as simple as an arithmetic routine, that is, one based on the axioms and theorems of arithmetic. How much should I tip the waiter? Or extremely elaborate and very deep mathematical frameworks like those embodied in general relativity and quantum mechanics. The latter kinds of models typically require years of study just to follow the arguments, never mind attaining the skills to solve some significant problems. When appropriately developed and harnessed, mathematical formulations possess enormous power. To many, this is a profound mystery. Years ago, Eugene Wigner, a most eminent mathematical physicist, wrestled with the question of what he deemed the unreasonable effectiveness of mathematics. And he concluded, and I'm quoting, "It borders on the mysterious, and there is no rational explanation for it." Bigner provides an anecdote with the following. A statistician was explaining to a non-mathematical friend the equation for the Gaussian or normal distribution, describing some characteristics of a population. The friend was skeptical and asked, "How can you know that? And what is that symbol there?" Oh, said the statistician, "that is pi." "What is that?" said the friend. "The ratio of the circumference of the circle to its diameter," the statistician replied. "Well now," said the friend, "you're pushing the joke too far. Surely the population has nothing to do with the circumference of a circle." Not only is it the case that mathematical concepts turn up in unexpected places, but physicists, engineers, and other scientists are able to develop mathematical models of extraordinary effectiveness, both in describing nature's contingencies and in predicting previously unobserved phenomena. I've discussed Wigner's mystery elsewhere in the context of historical shaping of abstraction of verbal behavior, but I'll not pursue that topic any further today. Mystery or not, there's no question of the potential value of a mathematical account. This, however, does not imply that all the phenomena could or even should be approached from a mathematical perspective. Indeed, some phenomena are simply not mathematically amenable or tractable. Now, a significant number of psychologists and laypersons alike are, to say the least, suspicious of, if not offended by, mathematizing the mind. In the words of John Keats, "Do not all charms fly at the mere touch of cold philosophy? Philosophy will clip an angel's wings, conquer all mysteries by rule and line, empty the haunted air and nomad mind, and unweave a rainbow." As many in this audience know, Skinner in his essay Flight from the Laboratory included a section entitled "The Flight to Mathematical Models." One of his concerns was that such models essentially neglected the reality of the findings of the laboratory. As he put it, no degree of disorder in the facts has placed any restriction on the elegance of the mathematical treatment. One is reminded of a story of a poor dairy farmer who, in desperation to find a way to increase the milk production of his cows, asked a mathematician for help. The mathematician thought for a while and then began, "Assume a spherical cow." However, Skinner did show considerable insight into what conditions might be needed for productive mathematical treatment of behavior analysis. As he says, first it must be made clear that the formal properties of a system of variables can be profitably treated only after the dimensional problems have been solved. He added, techniques are now available for the experimental analysis of very subtle behavioral processes, and this work is ready for the kind of mathematical theory that's always been productive at a certain stage in the history of science. What is needed is not a mathematical model, he says, constructed with little regard for the fundamental dimensions of behavior, but a mathematical treatment of experimental data. Mathematics will come under its own in the analysis of behavior when appropriate methods yield data which are so orderly that there's no longer any need to escape into a dream world. Indeed, the exquisitely refined techniques for conducting the experimental analysis of behavior are capable of yielding order and behavioral patterning to derive some data seen in a physics lab. Such orderliness virtually cries out for a quantitative analysis and beyond to the kinds of mathematical models seen in other fields dealing with complexity such as economics, ecology, physiology, and epidemiology. And it has surely come to pass that behavior analysis is to a large degree a quantitative enterprise, so much so that today it would be impossible to teach basic behavior analysis properly without at least some treatment of mathematical approaches and models. For example, as you all know, the topic of choice has and continues to be the stereotype of quantitative behavior analysis. If you go to the JAB Abstracts website and type in the keyword choice, nearly 500 references will be presented. This is but one journal, and even in that journal, the set is no doubt incomplete. The topic timing yields almost 1,000 references. Now, to be sure, not all of these reflect some mathematical treatment, but very many of them do. The future of the field promises much more of the same, and with growing sophistication, particularly in areas like stimulus control and behavior dynamics. Thus, the behavior analytic community, and especially, I believe, those currently being trained in the field, need to become much more aware of these developments. There are some hopeful signs. For one, the very fact that more of this work is being done by younger researchers bodes well for its significance and thus its future. Second, the success of the Society of the Quantitative Analysis of Behavior in attracting quite large and enthusiastic audiences at these ABBA meetings shows that many are interested in knowing more about the field and participating in its development. As already indicated, I'm going to treat the topic of models and methods and tools here for a bit. As already indicated, the world of mathematical modeling is huge. There are very, very many books on the topic. So how might one approach it? First, there are some general questions and issues that emerge from any consideration of a mathematical description of phenomena, including behavior. John Castee, who's written a number of books on mathematical modeling, has attempted to develop a model of models. That is a formal theory of models. Time doesn't permit any discussion of this work, but he raises some questions at the beginning of his formulation that you might think about as we examine some approaches and examples shortly. I'll be at least informally touching on some of these questions in this little talk. We need to define some criteria for what might be considered a model, in particular a good one. As I touch on the kinds of approaches math models have taken, we will see how formal descriptions are discovered and are derived. We'll also see there can be a battle of models vying to capture best the phenomena of interest. Of course, models contain variables and parameters that must in some way relate to actual measures, that is, observables. Adroitly choosing these is sometimes the most challenging aspect of effective modeling. Lastly, we'll see that models, especially mathematical models, typically do not stand alone. They're often products of other models by which variables and parameters are transformed into a new domain of measures and interpretations while maintaining a similar mathematical structure. How are models built? First, I cannot overemphasize that such activity has no algorithmic procedure or recipe. One simply follows and a fine model emerges like a roast chicken from the oven. As I've already indicated, this is a skill, and as with any skill worthy of the name, it must be acquired carefully and properly and practiced over and over. One typically learns the rudiments of various mathematics and science courses with many examples and problems. Given some background, you'll ultimately learn specific techniques from the very models of modern major modelers in one's field of interest by reading and working with examples of significant models in the literature. Here's outlined some of the common steps modelers take in formulating their models. As with any complex task, lists like this can be misleading in many ways, not the least of which in laying out a sequence of steps, when in fact the ordering may be quite mixed up and a good bit of parallel processing may be going on. Anyway, nothing interesting happens without identifying something calling for a model: choice, timing, delay, and so on. One major source is, of course, extant data properly organized that call for some formal representation and analysis. As already indicated, models demand assumptions, and it's at this stage that the special character of a mathematical model is revealed, for good or ill, and that specificity and clarity are absolutely essential. Otherwise, the construction of the model cannot go forward. The very limitations of these assumptions can confer enormous power to describe and draw implications from the analytic tools inherent in mathematical construction and manipulation. All of the theory of relativity, for example, is founded on but two assumptions: that the speed of light in a vacuum is a constant, and that the laws of physics do not depend on states of motion. Given a clever enough person, from these assumptions one can get atomic energy and a new formulation of gravity. The issue of interpretation is an important one and is often non-trivial. Certainly a set of mathematical symbols is meaningless without an interpretive context. Validation in the process of accounting for known data is an obvious criterion for a good model, but suggesting of new studies and predicting their results are the real marks of an effective model. Fundamentally, models of behavior attempt to describe and predict various behaviors under certain initial and boundary conditions and histories of these conditions. These are just a few dependent and independent variables commonly entering into mathematical models of behavior, and a few I'll try to illustrate a bit later. Not all variables entering into models are directly measurable, but are presumably tied to those that are. Skinner's reflex reserve, Nevin's behavioral momentum, Stadin's states, and the Rescorla-Wagner associative strength are examples. The invocation of such variables has been and continues to be controversial in behavior analysis. This is not the place to debate such issues, but theoretical variables are a common feature, and some would say an absolutely necessary feature of mathematical models, and their nature and roles in the development and interpretation of such models are important issues. By structure, I mean here a variety of aspects, including key variables and the assumptions underlying the phenomenon modeled. The static versus dynamic distinctions are about primary independent variables, but the issues go deep and sometimes distinctions are obscured. Many mathematical descriptions in behavior analysis focus on steady state or equilibrium conditions, typically prevailing after extended exposure to a given experimental arrangement. For example, the matching law and its derivative Herrnstein's hyperbola describe summary or steady state conditions prevailing between reinforcement rate and response rate. Dynamic models, in their most compelling form, would describe how behavior changes in real time with changes in the environment. For example, changes in reinforcement rate. Regarding the discrete versus continuous distinction, although Skinner in developing his methods came to digitize behavior, displays like cumulative records and summary data from operant studies tend to view behavior essentially as a continuous variable. In some ways, the so-called free operant carries the quality of continuity. Many models have adopted this perspective in that they formulate behavior as a continuous function of continuous variations in environmental conditions. What does continuous mean? Well, there are considerable technicalities here, but for present purposes it means a function that could be drawn without lifting one's pen off the paper. In general, continuous models can be formulated as differential equations, and I'll give some examples shortly. Discrete models are also common, particularly when one is interested in demarking episodes or trials and describing how behavior changes from episode to episode. The Rescorla-Wagner model of Pavlovian conditioning is a prime example where changes in associative strength are affected by what happens on a given trial, and this effect is carried to the next trial. Discrete models are formulated as what are called difference equations, typically. Various manifestations of computational models, for example, neural networks, are essentially difference equations formulations. Deterministic models are by definition those that explicitly contain no stochastic elements. Another way of expressing this is that for a given exact input, the output will always be exactly the same. Given the rules of arithmetic, 2 times 2 is always 4. Likewise, for a given set of parameters, Herrnstein's hyperbola will yield a precise value for the rate of responding given the rate of reinforcement. However, I should mention that there are important cases where a deterministic model will yield stochastic results, or sometimes called chaotic results. Time permitting, I'll show you an example later. Behavior, of course, is inherently variable, as is the environment in which it interacts. Skinner, in his theory of behavior, emphasized the effects of various conditions on the probability of responding and was led to adopt rate of responding as a measurable surrogate for that probability. Recently, Colleen and his colleagues have approached the theoretical variable of response strength in terms of various statistical techniques and have concluded that the best way to think about strength is a probability. The probability of making response conditional on the onset of a stimulus, on the passage of time from that stimulus, on the passage of time from the previous response. This analysis is then embodied into stochastic models of behavior, naming probability machines that generate, for example, inner response times, characteristics of various schedules. Models have many other features, some of which are only indicated here, and the list could be greatly extended, and I may touch on just a few of these in my examples. What problems have been addressed by mathematical models? Well, this list should not be surprising, and of course many more examples could be added. I'll just simply note that no area in basic behavior analysis has escaped some form of quantitative approach. So, what good is mathematics? At this point, I'd like to outline the sorts of areas or mathematical methods that have been commonly used in modeling behavioral phenomena. Of necessity, this will be a whirlwind tour and highly selective. We could spend all my allotted time on any one example. My intent is simply to give you a flavor of the variety of methods and the kinds of problems addressed. Here's a selection of methods commonly used in the quantitative analysis of behavior. I'll discuss some aspects of some of these, time allowing. Let me begin by talking about function properties and curve fitting. These are perhaps the crudest forms of mathematical modeling. Indeed, the procedures may not even merit the title of a model. However, done with care, they can suggest models to explore. Moreover, curve fitting is an inherent part of assessing any mathematical model. After all, such models are about functions, and functions have special signatures that allow for testing whether they are in conformity with data. I'll not discuss here the statistical technicalities of actual curve fitting techniques. Jack is going to talk about it later, I assume. But such procedures should be part of the toolbox for any mathematical modeler. I'm going to show a couple of figures that will be familiar to some of the people in the audience because I stole them out of their publications or got them from other sources, so I will acknowledge that at this point. Let me begin with an example of Herrnstein's matching law and Baum's generalization of it. Note that Herrnstein's approach in displaying order required a number of steps of particular relevance to modeling, including 1, conceptualizing the problem of distribution of behavior confronted with alternative sources of reinforcement, 2, selecting the variables of response and reinforcer frequency, 3, focusing on the proportion of responses and reinforcers on each alternative, in other words, the relative rates of responding and relative rates of reinforcement, and 4, plotting these proportions on a linear scale, thus showing, in this case, the equality of those values. Baum's modification was another exercise in curve fitting, but more sophisticated. The data obtained from choice experiments were often not in conformity with simple matching. A basic principle of modeling is if the model doesn't fit the relevant data, you got to change the model. It's clearly wrong. By representing matching as a power law and plotting it in log-log coordinates, the parameters of bias and sensitivity could be measured directly. Indeed, one can say that the concepts of bias and sensitivity essentially emerged from this analysis. This calls forth another essential element of quantitative analysis, namely data display. Transforming data by taking logarithms or arc sines or ratios or whatever and are selecting appropriate coordinate systems can sometimes make puzzling data into orderly functions. Here are the mathematical expressions characterizing the functions just displayed. Now, we might argue whether we're talking about real models here, never mind laws, but these expressions have encompassed an enormous number of results and have served well as ways of interpreting these results. Any creditable model of choice would have to confront these descriptions. Now, here's another example of curve fitting that has been discussed widely here, namely, what is the real discount or delay function? Curve fitting at its most basic is an exercise in local prediction. For example, if one was only interested in a quick and dirty description of some data over a specified interval, a polynomial will fit almost any set of data points given perhaps some prior data reduction. But such a representation is not a model, much less a theory. However, as already indicated, thoughtful selection of a function to fit data can lead to, or at least inform, a theoretical model. There's now some considerable literature on the mathematical form of the delay function. That is, how does the effect of a reinforcer on maintaining behavior depend on the delay between the behavior and the presentation of that reinforcer? One suggestion is a hyperbolic relation between reinforcer value and delay. This hyperbolic discounting function has enjoyed a fruitful history, especially in areas called self-control, and among other things, it has appeared to explain why, given a choice between a small but immediate reinforcer and a large but delayed one, just which would be chosen would depend on when the choice was made. Moreover, this discounting function is invoked to explain why variable schedule conditions may be preferred to fixed, even if they result in the same reinforcement rate. Now, other researchers claim the delay function should be exponential, but the data are not necessarily definitive in selecting just which, if either, is the real delay function. Here are some data fit with hyperbolic functions. Part of the difficulty here is that errors of measurement in behavioral data may not allow one to select with confidence one function over another. Such choices are generally made a priori as assumptions or derivatives of models or theories. To decide between possible functions, we need a theory. For example, if one were to show somehow that the same class of functions describe delay of reinforcement and remembering, or perhaps I should say forgetting, that might lead to more comprehensive theory of how delayed events affect behavior. If we assume for whatever reasons that, say, delay of consequences is described by a particular function, then that may be incorporated into models of other phenomena. Now I want to talk about the calculus. The calculus is one of the most important tools of mathematical modeling, and the topic lies at the foundation of a host of other methods, some of which I'll briefly describe later. Without question, the calculus is lingua franca of science, including fields like economics and ecology, so that without some familiar with it, most of science is in fact largely inaccessible except on a quite superficial level. The calculus also finds a natural home in behavior analysis because a core application is a quantitative description of change. Those of us who are old enough to have been steeped in cumulative records as compelling descriptions of behavior in motion, as it were, are particularly attuned to seeing calculus in pictures, displaying changes in response rate in time. In other words, patterns of behavior unfolding in time. As most, if not all, of this audience is aware, the slope of a cumulative record at any point measures the instantaneous rate of responding. Let's look at an arbitrary function, however. If we know a function, the calculus can tell us, in most cases, what the slope will be at any point where the function is defined. The method of finding slopes, that is, derivatives, also allows us to find how slopes themselves change with time. So, for example, we might be interested in how rate of responding itself is changing with time, what we would call the second derivative. Consider the case how response rate changes with respect to time in fixed interval schedules as opposed to variable interval schedules. Fixed interval schedules are said to engender accelerated responding, while variable interval schedules maintain a relatively constant rate. In other words, the second derivative is essentially zero. Another aspect of thinking in terms of the calculus is to see behavior and its patterning as a continuous function, somewhat like the motion of a body in a gravitational field. Viewing behavior as a continuous variable and thus to model patterns in time using the calculus is in general to treat behavior and its descriptions in molar terms. Indeed, this kind of thinking has led to a number of models of behavior based on mechanical, electrical, or chemical analogs, examples of models based on other models that I will talk a little bit about subsequently. Because the differential calculus is concerned with slopes, it has a special role in dealing with problems of optimality, one of the key ideas in the modeling of behavior. Note in this arbitrary functions points where the slope is zero. These are called stationary points, and two of these, B and Q, are at a local minimum and maximum respectively. Finding where the derivative is zero is an important step in determining where the function has peaks or valleys, local or perhaps even global optima. Here's an example. For a given ratio, how fast should a pigeon respond? One might assume as fast as possible, but responding, especially rapid responding, takes energy or effort. John Statton's model is based on a theoretical variable of cost, expressed in terms of two quantities: time between reinforcer presentations as a function of ratio value and rate of responding, and the cost of responding itself. Once this simple function is assumed, the rest is actually easy. Take the derivative of this cost function with respect to rate and set it equal to zero. Then solve for the rate. For a given ratio value and cost, we can now determine just what rate we would expect to see. The function itself shows that the rate should increase as the square root of the ratio size, which is a result consistent with some data. Optimality approaches using the methods just presented finds a point along a function where the function is a maximum or minimum, maybe local or global. Another more advanced method called the calculus of variations is used when one would like to know an optimal function, not a point, but a function. Perhaps the simplest possible example would be to find the function describing the shortest possible distance between two given points in a plane. Well, we would immediately guess it was a straight line, a linear function, and of course it'd be right. But if I ask you what function describes the shortest distance between two given points on a sphere or a saddle, that would not be so obvious. Here's a quick example from optimal foraging theory. How fast should a pigeon eat? One might think that a pigeon in the wild under significant food deprivation should, when encountering food, eat as fast as possible. A similar assumption we could have made with the ratio example. However, in terms of fitness, if the pigeon focused entirely on feeding, it might not see a hungry hawk swooping down to feed on it. A moment's reflection might lead one to guess that the pigeon would initially reduce its deprivation rapidly, then slow its intake while being more on the lookout for predators. Thus, to re-emphasize, we're talking about an optimal function here, not an optimal point. To determine just what this function is requires us to propose or assume a fitness function, somewhat like Staddon's cost function. The initial problem is to generate a reasonable loss of fitness function in relation to deprivation and then decide what to optimize. I'm not going to go through further details here, but the result yields a function that corresponds to our intuition, namely an exponential decay rate of eating. As a general point, the calculus of variations is truly one of the greatest ideas anyone ever had and is worth at least a lecture on its own. Interestingly, the method has been used very little in modeling and behavior analysis to my knowledge. Now I'm going to talk about differential equations. Equations that contain rates of change or derivatives are called differential equations. Most of the mathematical laws of nature, from planetary motion to predator-prey interaction, radioactive decay, enzyme kinetics, population dynamics, etc., 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 are derived or expressed as differential equations. These are equations that can express relations among continuous variables and their rates of change or derivatives. They embody the Heraclitean principle that all is flux. Newton's second law, which is a differential equation, says that any applied force is equal to the time rate of change of momentum. If one wanted to find the velocity or position of a particle as a function of time, one has to solve the differential equation subject to certain initial or boundary conditions. Ordinary differential equations and their solutions show, for example, how some variable changes continuously with time, or more generally how one variable changes continuously with respect to another. The field is huge. Many mathematicians spend their entire careers studying such equations, and students in some sciences and engineering may take several courses in this topic. Anyone who plans to do modeling very seriously should at least be reasonably familiar with the standard methods for setting up and solving such equations. Because differential equations are so important in modeling, time allowing, I want to mention a few examples. My emphasis here certainly reflects my own biases and training and is not necessarily a passionate plea that everyone interested in learning to model should take up the heavy cross of this huge field. As I've already indicated, or will indicate, the house of modeling in behavior analysis has many rooms. The examples are more in the nature of play than serious detailed models of complex phenomena, but I would argue that such play can be the source of interesting and perhaps even useful ideas. What we have here is a hypothetical experiment, but one that could be done. Imagine we set up a dual pigeon chamber with a clear partition between each bird. We arrange a contingency such that changes in the rate of responding of one pigeon changes the reinforcement frequency of the other pigeon. Here, for example, increased response rate for P1 reduces the reinforcement rate for the other pigeon, P2, thus reducing P2's response rate. That in turn reduces P1's reinforcement rate, reducing its response rate, which in turn leads to increasing the rate of reinforcement available to P2 and so on and so on. So we have a dynamic interplay between the birds that in fact has a counterpart in very simple predator-prey interactions. Now, how would things proceed? Well, let's look at an example that's unfortunately more familiar. Suppose William is in love with Zelda, but Zelda's a fickle lover. The more William loves her, the more she dislikes him. And when he loses interest in her, her feelings for him warm up. On the other hand, William reacts to her. When she loves him, his love for her grows, and when she loses interest, he also loses interest. Well, how will the course of true love be reflected? Well, not too well. In this case, William and Zelda are in a perpetual love-hate cycle, indeed loving each other only about a quarter of the time. The problem here is to understand the amplitude and phase relations between the interacting systems. Here's another example. Assume a spherical pigeon. Operant behavior is dissipative, requiring reinforcement to maintain it. Changes in behavior, for example, response rate, should be related to changes in the prevailing reinforcing medium, in other words, reinforcement frequency. According to Nevin's behavior momentum theory, a relatively higher reinforcement rate confers more mass to behavior, meaning that a disruptor, such as a change in reinforcement frequency, will exert relatively less effect on, say, rate of responding, even when initial response rates are equal. Put it another way, one must prefer to be struck by a feather moving at 50 miles an hour than a Mack truck going the same speed. Now, what I'm doing here is modeling a disruptor as a sudden change in the viscosity of a liquid, whose viscosity parameter is signified by eta, and have arranged two unequal masses to fall at the same velocity, v sub 0, into different media increased viscosity, but the viscosity is the same in the two cases. Now, both masses will reach terminal velocity. The greater mass with the higher velocity, just as Aristotle would have said. Here we have set up the arrangement for this differential equation, which will tell us what the terminal velocity is as a function of mass. If we solve this equation, we get an exponential function, which tells us that if you have one mass, for example, is twice as big as another, that larger mass will sustain a higher terminal velocity, or rate if you like, but will achieve that velocity at a little bit later time than the smaller mass, which will of course have much less of a terminal velocity. The ratio of times to reach terminal velocity and the ratio of velocities reached will be directly related to the ratio of the two masses. This should be in conformity with behavior momentum theory. In addition, such relations might apply to changes in response allocation in concurrent schedules when reinforcer allocations are changed. Another spherical pigeon. Speaking of concurrent schedules, here's a mechanical model of a two-choice contingency as a double well potential, and another spherical pigeon bouncing back and forth between the two wells, energized by deprivation and differential availability of food from the two sources. The potential function in a well will be proportional to the obtained reinforcement frequency. The deeper the well, the longer the bird will stay in it. This is another model based on another model. In this case, a model of a behavior system derived from the model of a mechanical system called a Dufing system. This could actually demonstrate chaotic behavior under certain conditions, and I'm not going to go into the details of that. The stochastic aspects of concurrent performance are still matters of debate, but here's how this system can behave, first under conditions of equal reinforcement frequency. Consider the top part as, say, side A, and the bottom part side B. And we have this pigeon hopping back and forth between these two sides. Note that the pigeon spends about equal times on both sides, but that the switches and dwell times have a stochastic quality, including, I think, some ambivalences. Now here's what happens when one well is made deeper than the other. That is, a higher rate of reinforcement is available for one alternative. Again, despite the apparent random aspects of performance, more time is spent on that side. As you can see, it spends most of the time there on the bottom, but with occasional forays into the top, somewhat like pigeons actually do in concurrent schedules. Now I'm going to skip over a bunch of stuff here in the interest of time. As indicated earlier, physical systems can have been quite useful in developing quantitative models of behavior. Developing these models also depended on clear understanding and intuitions about behavioral processes and associated functional relations. On the one hand, there's no reason to expect that any given physical system, especially a simple one, would necessarily provide much insight into the subtlety and complexity of behavior dynamics. On the other hand, seeing possible useful connections between putatively different systems may be essential to sophisticated developments in the quantitative theories of behavior. At any rate, in many cases, we don't know how to write a differential equation to define the system, but there are other tricks we can use that depend on thinking about organisms, for example, as a black box that transforms inputs, for example, reinforcer presentations, into outputs, responses. McDowell and Kessel and Pallier and others have developed the method of linear systems theory for application to both equilibrium schedule performance and to conditions of transitions between reinforcement contingencies. One result is this multivariate rate equation, which corresponds to Herrnstein's hyperbola, but in fact can handle more kinds of situations and data. Let me just say a word about difference equations. Difference equations are discrete counterparts of differential equations. Many in this audience are familiar with the difference equation model of Pavlovian conditioning, namely the Rescorla-Wagner model. The model shows trial-by-trial changes in associative strength as conditioning proceeds and provides an account of several phenomena such as blocking and overshadowing and so on and so forth. It cannot account for or otherwise fail to deal with other phenomena. It has been superseded by a number of other successful models, as we've seen here at this meeting. There are very many examples, and the use of these models is rapidly increasing. Basically, difference equations are examples of what are called iterated function systems. For example, an initial value is assigned to a function, and this yields a new value. This is returned to the function to yield yet another value, and so on. One question is whether such a procedure will ultimately produce stable or fixed point value, like the asymptotic associative strength in the Rescorla-Wagner model. These methods are natural for computing. Indeed, many absolutely require computing routines, and there's a large class of models called appropriately computational models. And here are a few examples. There are other computational systems that may be less well known by behavior analysts, but have some potential value to them. These go by several names, including dynamic state variable models, adaptive dynamics, dynamic programming, and so on. Much of this work is focused on behavioral ecological settings and is based on some expression of optimality. For example, an organism is faced with opportunities to explore food patches and to reproduce, but it's also faced with predators and with uncertain variations in food resources. One assumes that the organism acts so as to maximize fitness, that is, to produce the most offspring. By setting these various conditions of trade-off between starvation, predation, and reproduction into difference equations, one can track from time epoch to time epoch probabilities of survival under different strategies. For example, given a choice between random selection of patches and some optimal choice, the models can demonstrate the value of optimal selection on the probability of reproductive success. Here are some examples of Killeen's IRT machines as indications of stochastic models. Now, I've mentioned earlier the powerful role of stochastic modeling in behavior analysis, and here is an example with his machines. And because time is short, I'm told, I will not go into further details. Today I've tried to give you a flavor and scope of mathematical modeling applied to behavior analysis. For those of you for whom most of this was old stuff, I hope you weren't too bored, but then this talk clearly wasn't for you anyway. For those of you for whom much of this was new, I hope you might become interested in learning more about what mathematical modeling is good for, and even perhaps try some of it yourself. The practice is actually a kind of game, and for the most part in this field, any given model shouldn't be taken too seriously. All models are wrong. The issue is how good they are for present conditions and purposes. Many concepts and approaches in the analysis of behavior, and certainly psychology in general, are powerfully seductive. And like too many seductions, we may be led astray. Modeling is clearly a game to be played with humility as well as fun. I note the following sort of trap. This is a compelling example of hopping to conclusions. Thank you very much for your time.